In this video, our last video on polymers, we're going to talk about some more trade-oriented kinds of polymers and some of their properties. So let's start with this one. Now this one looks like a mouthful. It's part of a class of polymers that are heat or fire resistant. It's called polytetrafluoroethylene, otherwise known as Teflon. Now, Teflon has been used for decades for a variety of different purposes. We most commonly think of Teflon when we think of non-stick cookware. It's the stuff that is sprayed onto metal to create a slippery surface that makes it hard for other food to stick on. But it's been used for a variety of different purposes other than that. Things like it's a very strong polymer, so it's been used for tubing and gaskets. It's been used for valves. It's been used for a number of different slippery kinds of surfaces. We find when it's rolled into tape, it provides a pretty good seal for threaded items like faucets or so you see Teflon tape used in plumbing oftentimes. Other things that are important for it, it's extremely heat resistant and it's quite unreactive, which again is why it's used in cookware. Now this is a similar kind of, it's in that same vinyl kind of class of polymers. The only difference is we talked about how there were hydrogens attached to the carbons in each of these cases. This is not the case for Teflon. Teflon has fluorine atoms in each one of those cases. So that's where the tetra comes from. Tetra is a prefix that means four. So 4-fluorine ethylene. And that's what this structure is. Now, as a result of that, when Teflon does burn, or when it does decompose, it does give off fluorine and fluoride compounds, which can be pretty nasty. Another common commercial polymer is something called Nomex. Nomex is a heat-resistant fabric. We see it often used in fire suits. We also see Nomex in things like the suits that race car drivers wear to protect them from in case a fire breaks out in their car. And the reason why is when it is exposed to intense heat, it begins to carbonize and thicken. The carbonization helps in the creating a structure that is more resistant to burning. And the thickening provides a method of insulation to protect the person that's inside. Now, another type of commercial polymer is something called Kevlar. Kevlar originally was thought of for having a flame-proof kind of disposition, but what we've seen with Kevlar through other types of extensive research is that when it is drawn into fibers and woven together, it actually creates a fabric that has a tensile strength greater than that of steel, while at the same time being extremely light. And so we've seen Kevlar used for different types of armor, for bulletproof vests, for puncture-resistant vests and armaments, and that's the reason why. And so the last commercial product that we're going to look into is rubber. And rubber is a very, very common, well-known polymer. But on its own, rubber is kind of a weak polymer. Rubber is the result of a sap. It's a sap from a particular tree that grows primarily in the tropics. And the sap itself is kind of sticky, not very stretchy, not very really anything that resembles rubber. But when it's vulcanized, when we introduce those sulfur crosslinks, then we get a whole lot of elasticity and a good measure of hardening. Now, the process of vulcanization, which was developed in the 1800s by a man by the name of Charles Goodyear, who later on went to have enormous success turning that process into the casting and production of rubber tires, is a rather interesting one. You take natural rubber, you heat it up with elemental sulfur, and the sulfur starts to build these cross-link bridges between the rubber polymers and gets the rubber to harden and solidify. And then once it's vulcanized, then you can take that rubber and put it into shapes, and have it do whatever it is that you need to do. So most rubber products, whether they are rubber-soled shoes, rubber hoses, um, rubberized rollers or jackets, tires, these all are substances that are vulcanized in some kind of capacity. Now, they may have different varying degrees of vulcanization depending upon their bendability, their strength, and what you're trying to get out of them. But they've all been vulcanized in some way. There are no natural rubbers that are in use that haven't been vulcanized to some degree, because natural rubber is really kind of useless as far as a material is concerned. Now, again, the amount of sulfur that is used, how much it is vulcanized, gives a natural, gives us an idea of how soft and or elastic or sturdy and rigid a product is going to be. Now, about a third, a little bit more than a third, 35% of all of the rubber that is out there and all that is needed, it comes from those natural tree sources. Most rubber nowadays, though, it has been synthesized, and so we get elastomers that are not rubber, not synthetic rubber necessarily, in terms of they don't have the same chemical formula and structure, but they've been designed and engineered to have very, very similar properties. And so those generally are thought of and described as synthetic kinds of rubber. Now, when it comes to rubber and rubber products, we can see that there are a couple of different types. Styrene butadiene rubber, SBR. This is the type of raw material that ultimately becomes a tire. Neoprene rubber, which should be familiar to most of you. This is a substance that is found in a lot of different kinds of rubbers, especially rubbers that are going into shoes and other things. And it's valued because it is chemically resistant to petroleum products, and it's chemically resistant to ozone, which makes it really good for being out in the environment. Now, what happens when that rubber burns? Well, now you've got all this vulcanized rubber, you've got all those sulfurs trapped in the structure. The big primary issue with vulcanized rubber is the release of that sulfur when it burns. Sulfur dioxide is by far the more dangerous byproduct of this burning process. Carbon monoxide also comes off, and obviously that's nasty as well. But as with all polymers, you get a whole lot of dense smoke because you've got a whole bunch of carbon that is trying to burn but can't burn completely. And so you get all of this ash, all of this soot, and contained in that soot are these substances that are really, really nasty. Now, neoprene, which we mentioned previously, it has chlorines in it in addition to the sulfurs. And so you get hydrogen chloride gas in that mix as well, which obviously hydrogen chloride gas, HCl, when it comes into contact with water, turns into hydrochloric acid, which is corrosive and nasty, and you definitely don't want to breathe it in. So the last image that we're going to leave with in this particular unit is this one. This is a tire fire, a literal tire fire. And this is at a landfill, and the book speculates that This is likely started as a result of a lightning strike in the field. So lightning strikes the tire pit here. It catches some of the tires on fire as a result of that energy, and then the heat and the energy that result from that fire cause the other tires to ignite as well. But look closely. Obviously, this is a hot fire. This is, quite ominous looking. But look closely at that smoke as well. Look how dense it is. Look how thick and black it is. That gives you a lot of information in terms of just how much is left over and left behind when these kinds of polymers burn. And this is never going to be completely combusted. This is going to get released up into the upper atmosphere, and the sulfur that is in here will probably come back down as acid rain. But if you're anywhere near this, it's going to smell. Not only is it's going to smell bad, it's going to have that sulfur burning hair kind of smell that can just kind of choke you out as it goes. So you've got to be really careful. If you're one of the guys that's in this class that is a first responder, be especially careful when it comes to things that are involving sulfur and sulfur combustion, because sulfur dioxide in particular is a nasty substance, and when you breathe it in, it kind of grabs you by the throat and it doesn't let go. So be really careful. But this concludes for us polymers and the polymer unit here. So until next time, have a good day.